Fire, it is the oldest companion of humankind. It is the force that cooked our food, forged our weapons, lit our cities, and reshaped the surface of the entire planet. It is beautiful, it is terrifying, it is absolutely essential. And yet, despite living alongside fire for hundreds of thousands of years, most people know almost nothing about its true nature, its hidden behaviors, and the astonishing secrets it still holds. Today, we are going to change that. We are going to walk straight into the flames and uncover 100 of the most surprising, jaw-dropping, and mind-bending facts about fire that you have probably never heard before. From the chemistry burning inside a simple candle, flame, to the monstrous firestorms that consume entire forests in minutes, from the bizarre fires that burn underwater to the flames that rage on distant planets millions of miles from Earth. This is a journey through the full, extraordinary story of fire itself. Please let us know in the comments where you are watching this video and what time you are watching it, and be sure to subscribe to the channel for future videos. Now, let us begin. When you look at a candle flame, you might think you are seeing something simple. A wick, a bit of wax, a gentle flicker of yellow light. But what you are actually witnessing is one of the most complex chemical chain reactions in all of nature. Inside that tiny flame, there are thousands of individual chemical reactions happening simultaneously. The wax is melting, traveling up the wick through capillary action, vaporizing into a gas, breaking apart into smaller hydrocarbon molecules, mixing with oxygen from the surrounding air, and then combusting in a rapid oxidation process that releases photons of light and waves of heat. All of this is happening in a space no larger than your fingernail. Scientists have spent decades studying candle flames, and even today there are aspects of their behavior that are not fully understood. A single candle flame contains roughly 1 million individual chemical reactions every single second. That tiny, quiet little flame sitting on your dinner table is a miniature chemical factory operating at an almost incomprehensible scale. And here is something that will truly surprise you. A candle flame is not one uniform color. If you look closely, you will see that the base of the flame near the wick is blue. Just above that, it turns a darker orange, and at the very tip, it becomes a bright, luminous yellow before tapering off into a thin wisp of smoke. Each of these color zones represents a different temperature and a different phase of the combustion process. The blue zone at the base is where the wax vapor first meets oxygen. It is the hottest part of the flame, reaching temperatures of around 1,400 degrees Celsius, which is roughly 2,550 degrees Fahrenheit. The yellow part of the flame, which most people assume is the hottest, is actually cooler. The yellow color comes from tiny particles of carbon, called soot, that are heated until they glow, a process known as incandescence. These glowing soot particles are what give a candle its warm, golden light. Without them, the flame would be almost entirely blue and far less visible. Now, speaking of color, fire does not have a single color. The color of any flame depends entirely on what is burning, how hot it is, and what chemical elements are present in the fuel. This is why a wood fire glows orange and red, a gas stove burns blue, and fireworks explode in greens, reds, purples, and whites. Each color is produced by a different element. Copper compounds produce green and blue flames. Strontium creates a deep, vivid red. Barium gives off a pale green. Sodium produces the intense yellow-orange that you see in many bonfires and campfires. Potassium burns violet. Lithium produces a striking crimson. And magnesium burns with a blinding white light so intense that it can cause permanent eye damage if you stare at it directly. Chemists and pyrotechnicians have spent centuries learning how to manipulate these colors, combining different metallic salts and chemical oxidizers to produce the dazzling displays that light up the sky during celebrations around the world. Every firework you have ever seen is essentially a carefully engineered chemical fire, designed to burn specific elements at specific temperatures in a specific sequence. But color is only the beginning of fire's complexity. Let us talk about something even more fundamental, what fire actually is. This might sound like a strange question. Everyone knows what fire is, right? It is hot, it is bright, it burns things. But when scientists tried to classify fire, they ran into a genuine philosophical and scientific problem. Fire is not a solid, it is not a liquid, it is not exactly a gas either. And it is not a plasma, although under extreme conditions, flames can become plasma. So what is it? The answer is that fire is a chemical process, specifically a rapid, self-sustaining exothermic oxidation reaction. It is not a thing in the way that a rock or a glass of water is a thing. It is an event. It is something that happens, not something that exists independently. When you look at a flame, you are watching chemistry in real time. You are seeing molecules being torn apart and reassembled, energy being released as light and heat, and gases swirling in complex convection patterns. Fire is a process, and that distinction is important because it explains why fire behaves in ways that no solid, liquid, or gas ever could. One of those behaviors is the fact that fire needs three things to exist, and if you remove any one of them, the fire dies immediately. These three things are fuel, oxygen, and heat. Scientists call this the fire triangle, and it is the most fundamental concept in all of fire science. Fuel is anything that can burn: wood, paper, gasoline, natural gas, even certain metals. Oxygen is the oxidizer that allows the combustion reaction to proceed, and heat is the energy needed to raise the fuel to its ignition temperature and keep the reaction going. Take away the fuel and the fire has nothing to consume. Take away the oxygen and the chemical reaction cannot proceed. Take away the heat and the temperature drops below the ignition point. Every fire suppression method ever invented works by attacking one or more sides of this triangle. Water cools a fire, removing heat. A fire blanket smothers a fire, cutting off oxygen. And a firebreak removes fuel by clearing away burnable material. Understanding the fire triangle has saved countless lives, and it remains the foundation of every fire safety protocol in the world. But the fire triangle, as important as it is, was eventually found to be incomplete. In the 20th century, fire scientists realized that there was a fourth element necessary for fire to sustain itself: a chemical chain reaction. Without this chain reaction, fire would ignite for a brief moment and then immediately go out. The chain reaction is what allows fire to keep burning once it starts. In this process, the heat from the initial combustion breaks apart more fuel molecules, which then react with oxygen, releasing more heat, which breaks apart even more fuel molecules, and so on in a self-perpetuating cycle. This discovery led to the replacement of the fire triangle with a new model called the fire tetrahedron, a four-sided pyramid with fuel, oxygen, heat, and the chemical chain reaction each occupying one face. Some modern fire suppression agents, like certain halon-based extinguishers, work specifically by interrupting the chemical chain reaction rather than by removing heat, oxygen, or fuel. They break the cycle at the molecular level, stopping the fire from feeding itself. Here is something fascinating that most people never consider. Fire is actually a relatively rare phenomenon in the natural world. For most of Earth's history, there was no fire at all. Fire requires atmospheric oxygen at a concentration of at least 16% to sustain combustion. For the first 2 billion years of Earth's existence, the atmosphere contained almost no free oxygen. It was not until photosynthetic organisms, first cyanobacteria and later plants, began pumping oxygen into the atmosphere that fire became possible. The earliest evidence of fire on Earth dates to approximately 470 million years ago, during the Ordovician period. This evidence comes in the form of fossilized charcoal, which can only be produced by the combustion of organic material. So for roughly the first 4 billion years of our planet's 4.5 billion year history, fire simply did not exist. It could not exist. There was nothing to burn and no oxygen to burn it with. Fire is, in a very real sense, a product of life itself. Without living organisms to produce oxygen through photosynthesis, our planet would be a fireless world, and yet, once fire arrived, it changed everything. Wildfire became one of the most powerful forces shaping the surface of the Earth. Long before humans ever struck a spark, lightning was igniting massive natural fires that swept across ancient landscapes, burning away old growth, clearing space for new vegetation, and cycling nutrients back into the soil. Many ecosystems that exist today are not just tolerant of fire, they are completely dependent on it. Certain species of pine trees, for example, produce cones that are sealed shut with a thick layer of resin. These cones, called serotinous cones, can remain closed for years or even decades, protecting the seeds inside from insects, disease, and harsh weather. They will only open when exposed to the intense heat of a wildfire. The fire melts the resin, the cones crack open, and the seeds fall to the freshly cleared, nutrient-rich ground below. Without fire, these trees literally cannot reproduce. The entire species depends on periodic burning to survive. Grasslands are another ecosystem that owes its existence to fire. In many parts of the world, vast savannas and prairies are maintained not by rainfall or soil type, but by regular burning. Fire kills young trees and shrubs, preventing them from taking over, while grasses, which have their growing points at or below the soil's surface, survive the flames and quickly regrow. Without periodic fire, many grasslands would eventually be overtaken by forests. Scientists who study these ecosystems have found that when fire is suppressed, when humans prevent natural fires from burning, the landscape changes dramatically within just a few decades. Trees invade the grassland, biodiversity declines, and the unique community of plants and animals that depend on the open grassland habitat disappears. Fire in these environments is not a destructive force. It is a creative one. It is the gardener that maintains the garden. Some plants have evolved even more extraordinary adaptations to fire. The Australian eucalyptus tree, for example, has bark that peels away in long, dry strips that are highly flammable. When a fire arrives, these strips ignite easily and are carried by the wind ahead of the fire front, spreading the blaze to new areas. The eucalyptus tree benefits from this because its competitors, species that are less fire-tolerant, are killed by the intense burning. Meanwhile, the eucalyptus itself survives because it can resprout from specialized buds hidden beneath its thick bark or from underground root systems called lignotubers. In effect, the eucalyptus has evolved to encourage fire because fire eliminates its competition. It is one of nature's most cunning survival strategies, and it has made eucalyptus forests some of the most fire-prone landscapes on the planet. There's a grass in southern Africa called the fire lily that takes this adaptation to an almost poetic extreme. For most of the year, the fire lily is invisible, just a dormant bulb buried in the soil, showing no sign of life above ground. But within days of a wildfire sweeping through the landscape, the fire lily erupts from the charred earth in a blaze of brilliant red and orange flowers. The heat and chemical signals from the fire trigger the bulb to break dormancy, and the cleared, ash-enriched soil provides the perfect conditions for rapid growth. The fire lily blooms, is pollinated, sets seed, and then retreats underground again, waiting for the next fire. Its entire life cycle is synchronized with burning. Without fire, it would never flower at all. Now let us turn from the natural world to the human one, because the story of fire and humanity is one of the most important stories in all of history. The earliest evidence of controlled fire use by human ancestors dates to approximately 1 million years ago, although some researchers believe it could be even older. Sites in southern Africa and the Middle East have yielded hearth-like structures, layers of ash, and burnt bones that suggest early hominins, likely Homo erectus, were using fire deliberately. This was not the accidental encounter with a lightning-struck tree. This was the intentional maintenance and use of fire for cooking, warmth, and protection. The mastery of fire was arguably the single most transformative event in human evolution. It changed our bodies, our brains, our social structures, and our place in the natural world. Consider cooking. Before fire, our ancestors ate raw food, raw meat, raw tubers, raw plants. Raw food is harder to chew, harder to digest, and yields fewer calories than cooked food. Cooking breaks down tough fibers and complex proteins, making nutrients far more accessible to the digestive system. The anthropologist Richard Wrangham has argued persuasively that the advent of cooking led directly to a reduction in the size of our teeth, jaws, and digestive tracts, and a corresponding increase in the size of our brains. In other words, fire cooked our food, and cooked food made us human. The energy surplus provided by cooked meals freed up biological resources that were redirected to brain development. Without fire, we might never have evolved the large, complex brains that define our species. We are, in a very real and biological sense, creatures of fire, but cooking was only one benefit. Fire also extended the day. Before fire, human activity was largely limited to daylight hours. Once the sun set, the world became dark, dangerous, and cold. Predators roamed freely in the darkness, and early humans were forced to seek shelter and wait for dawn. Fire changed all of that. A campfire provided light, pushing back the darkness and creating a safe, illuminated space where people could gather after sunset. This extended the productive day by several hours and created something entirely new: leisure time. Anthropologists believe that the campfire was the birthplace of human culture. Sitting around a fire in the evening, early humans told stories, shared knowledge, strengthened social bonds, and developed language. The campfire was the original social network, the original classroom, the original theater. It brought people together in a way that nothing else could, and the social behaviors that emerged around the fire shaped the development of human civilization for hundreds of thousands of years. Fire also gave our ancestors a powerful weapon against predators. A burning torch or a ring of fire around a campsite kept lions, hyenas, wolves, and other dangerous animals at bay. Most wild animals instinctively fear fire. They associate it with the destructive wildfires that periodically sweep through their habitats, and they flee from the heat and light. Early humans exploited this fear ruthlessly. With fire, a small group of relatively weak, slow, and poorly armed primates could hold off predators many times their size and strength. Fire was the great equalizer, and it gave our ancestors the security they needed to sleep on the ground, to move into new territories, and eventually to spread across the entire globe. The ability to control fire also allowed humans to colonize cold environments. Without fire, our species, which evolved in the warm tropics of Africa, would never have been able to survive in the freezing climates of northern Europe, Central Asia, and the far north. Fire provided warmth in caves and shelters, making it possible to endure harsh winters. It allowed people to dry and preserve meat, tan hides for clothing, and harden the tips of wooden spears. Fire was the technology that unlocked the rest of the planet for human habitation. Every time you see images of ancient humans in Ice Age landscapes, remember that those people were only there because of fire. Here is another fact about ancient fire use that will surprise you. Early humans did not always know how to start a fire. For tens of thousands of years, possibly hundreds of thousands of years, our ancestors could use fire but could not create it from scratch. They relied on natural fire sources, lightning strikes, volcanic activity, spontaneous combustion in peat bogs, and then carefully maintained those fires, keeping them burning continuously, sometimes for years or even generations. Losing the fire was a catastrophe. If the group's fire went out and they could not find a new natural source, they were suddenly without warmth, protection, and the ability to cook. Some researchers believe that the role of firekeeper was one of the most important and prestigious jobs in early human groups. The person who tended the fire held the survival of the entire community in their hands. The invention of fire-starting technology, the ability to create fire at will, was a quantum leap in human capability. The two oldest methods are percussion and friction. In the percussion method, a hard stone like flint is struck against another stone or a piece of iron pyrite, producing a shower of hot sparks. If those sparks land on dry tinder, shredded bark, dried fungus, fine grass, they can ignite a small ember, which is then carefully nurtured into a flame. This technique dates back at least 40,000 years and possibly much earlier. In the friction method, a pointed stick is rapidly rotated against a flat piece of wood, generating heat through friction until the wood dust reaches its ignition temperature and begins to smolder. Variations of this technique, the hand drill, the bow drill, the fire plow, have been used by cultures around the world for millennia. Both methods require skill, patience, and the right materials. They are far harder than they look, and modern people who attempt them for the first time often fail repeatedly before succeeding. The modern match, which we take completely for granted, is actually a remarkably recent invention. The first friction match was created in the early 19th century, only about 200 years ago. Before that, starting a fire required flint and steel, a burning lens, or one of the ancient friction methods. The early matches were dangerous and unreliable. They used white phosphorus, a highly toxic substance that caused a horrific occupational disease among match factory workers called Phossy jaw. Prolonged exposure to white phosphorus fumes caused the jawbone to rot and glow a sickly greenish white in the dark. Workers literally had glowing, decaying jaws. The condition was painful, disfiguring, and often fatal. It was not until the development of safety matches, which replaced white phosphorus with the much less toxic red phosphorus, that match production became reasonably safe. The safety match, which can only be ignited by striking it against a specially prepared surface on the matchbox, was a major improvement and remains the standard design to this day. Now let us talk about something truly strange: fire in zero gravity. On Earth, fire behaves the way it does largely because of gravity. When a candle burns, the hot combustion gases rise because they are less dense than the surrounding cool air. This creates an upward flow called convection, which draws fresh oxygen into the base of the flame and gives the flame its familiar teardrop shape. But in space, aboard the International Space Station, there is no gravity. There is no up for the hot gases to rise toward, and so fire behaves in ways that look genuinely alien. In microgravity, a candle flame does not form a teardrop. Instead, it forms a perfect, hovering sphere. The flame is smaller, dimmer, and burns at a lower temperature than its earthly counterpart. It glows a faint, almost ghostly blue instead of the warm yellow we are used to. The spherical shape occurs because, without convective currents, oxygen reaches the flame equally from all directions, and the combustion products, carbon dioxide and water vapor, spread outward in a uniform shell. It is one of the most beautiful and counterintuitive demonstrations in all of physics, and it has taught scientists an enormous amount about the fundamental nature of combustion. Research aboard the space station has also revealed a type of fire that has no equivalent on Earth, a phenomenon called cool flames. In certain microgravity experiments, scientists observed fuel droplets that appeared to stop burning. The visible flame went out, there was no light, and the temperature dropped well below what is normally needed for combustion. But the fuel was still being consumed. Invisible, flameless combustion was continuing at temperatures as low as 300 to 600 degrees Celsius, far below the 1,000 plus degrees of a normal flame. These cool flames are sustained by exotic chemical reactions that are normally overwhelmed by the intense heat of conventional burning. In the gentle, buoyancy-free environment of space, these delicate reactions can sustain themselves and consume fuel without producing a visible flame. The discovery of cool flames has profound implications for fire safety in spacecraft and for our fundamental understanding of how combustion works. Back on Earth, let us talk about one of fire's most dramatic and terrifying manifestations, the wildfire. Wildfires are not gentle, predictable things. They are dynamic, unpredictable, and under the right conditions, they can generate their own weather. Large wildfires release so much heat that they create powerful updrafts of hot air. These updrafts can reach speeds of over 100 miles per hour and rise thousands of feet into the atmosphere. As the hot air rises, it draws in cooler air from the surrounding area, creating powerful winds that blow toward the fire from all directions. This self-generated wind system feeds the fire with fresh oxygen, causing it to burn even more intensely, which creates even stronger updrafts, which draws in even more wind. It is a feedback loop of incredible destructive power, and under extreme conditions, this process can produce something truly horrifying: a fire tornado. A fire tornado, also known as a fire whirl or fire devil, is exactly what it sounds like: a spinning vortex of fire. Fire tornadoes form when intense heat and turbulent wind conditions combine to create a rotating column of air that draws in flames. Small fire whorls, just a few feet tall, are relatively common in large wildfires and structural fires, but on rare occasions, fire tornadoes can grow to monstrous proportions. The largest recorded fire tornadoes have reached heights of over 1,000 feet, with wind speeds exceeding 150 miles per hour and internal temperatures above 2,000 degrees Fahrenheit. These are not metaphorical tornadoes. They are actual rotating vortices that can uproot trees, flip vehicles, and destroy buildings. They are among the most terrifying natural phenomena on the planet. One of the most destructive fire tornadoes in recorded history occurred during the Great Kanto earthquake of 1923, which devastated the city of Tokyo and the surrounding Kanto region of Japan. The earthquake struck at lunchtime, when thousands of cooking fires were burning in homes across the city. The quake toppled stoves and ruptured gas lines, igniting fires throughout the densely packed wooden neighborhoods. As the fires merged and grew, they generated intense heat that created powerful updrafts. In the Hifukusho Auto area, which was an open military clothing depot where tens of thousands of people had gathered to shelter from the fires, a massive fire tornado formed. The vortex swept through the packed crowd, killing an estimated 38,000 people in a matter of minutes. It remains one of the single deadliest fire events in human history, and it demonstrated with terrifying clarity the power that fire can achieve when it is unleashed on a massive scale. Wildfires can also produce another atmospheric phenomenon called a pyrocumulonimbus cloud, which is sometimes referred to as a fire thunderstorm. When a wildfire is large and intense enough, the column of superheated air it produces can rise so high into the atmosphere that it begins to behave like a thunderstorm. Moisture in the rising air condenses, forming a towering cumulonimbus cloud that can reach heights of 40,000 feet or more. These fire-generated thunderstorms can produce lightning, which can ignite new fires miles away from the original blaze. They can also produce strong, erratic winds that change the direction and speed of the fire without warning, making it extremely dangerous for firefighters. In some cases, pyrocumulonimbus clouds have even been observed producing their own rain, but the air below the cloud is often so hot and dry that the raindrops evaporate before they reach the ground, a phenomenon called virga. So the fire creates a thunderstorm that produces rain that never arrives. It is as if the fire is mocking our attempts to extinguish it. Now let us explore something equally dramatic but far less well-known: underground fires. Not all fires burn on the surface. Some burn beneath it, hidden from view, consuming fuel that lies underground. Coal seam fires are among the most persistent and difficult to extinguish fires on the planet. A coal seam is a layer of coal buried in the earth, sometimes just a few feet below the surface, sometimes hundreds of feet down. When a coal seam catches fire from lightning, spontaneous combustion, or human activity, it can burn for decades, centuries, or even longer. The fire smolders slowly through the underground coal, producing toxic gases, causing the ground above to subside and collapse and radiating heat that can make the surface too hot to walk on. There is a coal seam fire burning right now beneath the town of Centralia, Pennsylvania, that has been burning continuously since 1962. That is over 60 years of non-stop subterranean burning. The fire started when a trash fire in an open pit ignited an exposed coal seam. Despite numerous attempts to extinguish it, the fire spread through the vast network of abandoned coal mines beneath the town, and it has been burning ever since. The fire releases toxic carbon monoxide and carbon dioxide through cracks and sinkholes, and the ground above is dangerously unstable. Almost the entire population of Centralia has been relocated. What was once a thriving community of over 1,000 people is now a near ghost town, its streets cracked and steaming, its buildings demolished, its zip code officially revoked. And the fire continues to burn. Experts estimate that there is enough coal beneath Centralia to fuel the fire for another 250 years, but Centralia is not unique. There are thousands of coal seam fires burning around the world right now, at this very moment. Some have been burning for centuries. A coal seam fire at Burning Mountain in New South Wales, Australia, is believed to have been burning for approximately 6,000 years, making it the oldest known fire on Earth. 6,000 years. That fire was burning when the ancient Egyptians were building the pyramids. It was burning when the first cities were being founded in Mesopotamia. It has been burning for the entire span of recorded human history, and it shows no signs of stopping. These underground fires are not just curiosities, they are significant contributors to air pollution and greenhouse gas emissions. Collectively, the world's coal seam fires release hundreds of millions of tons of carbon dioxide into the atmosphere each year, rivaling the emissions of some industrialized nations. Let us shift our attention to something completely different, the science of how fire spreads through a building. Structural fires behave very differently from wildfires, and understanding their behavior has been critical to saving lives. When a fire starts in a room, say, from a faulty electrical outlet or an unattended candle, it initially burns slowly, consuming the material closest to the ignition point. The fire grows, producing heat and smoke that rise to the ceiling and begin to spread across the upper portion of the room in a hot layer of gases. As the fire grows larger and the temperature in the room increases, the radiant heat from the flames and the hot gas layer begins to heat all of the other combustible materials in the room: furniture, curtains, carpet, bedding. These materials begin to release flammable gases through a process called pyrolysis, even though they have not been directly touched by the flames. The room fills with these invisible, flammable gases, and the temperature continues to climb. And then in a single explosive instant, everything in the room ignites simultaneously. This is called flashover, and it is one of the most dangerous moments in any structural fire. Flashover occurs when the temperature in the upper portion of the room reaches approximately 500 to 600 degrees Celsius, or about 930 to 1,100 degrees Fahrenheit. At this temperature, the radiant heat is so intense that every combustible surface in the room reaches its ignition point at essentially the same time. The room goes from a localized fire to a fully involved inferno in seconds. Before flashover, a person in the room might have a chance to escape. After flashover, survival is virtually impossible. The temperature in a fully flashed-over room can exceed 1,100 degrees Celsius, hot enough to melt aluminum. Firefighters are trained to recognize the warning signs of impending flashover: darkening smoke, increasing heat, rollover of flames across the ceiling, and to evacuate immediately when these signs appear. There's another deadly fire phenomenon that firefighters must watch for called backdraft. A backdraft occurs when a fire in an enclosed space consumes all of the available oxygen, causing the fire to die down or go out. But the room remains extremely hot, and it is filled with unburned, superheated combustible gases. If someone opens a door or window, admitting a sudden rush of fresh oxygen, those gases can ignite in a violent, explosive fireball that blows outward through the opening. Backdrafts have killed many firefighters who unknowingly opened doors into oxygen-depleted rooms. The signs of a potential backdraft include smoke-stained windows, smoke pulsing around door frames as if the room is breathing, and windows that are hot to the touch. Experienced firefighters learn to read these signs and to ventilate such rooms carefully and strategically to prevent explosive reignition. Now, here is a fact that will change the way you think about house fires. The amount of time you have to escape a house fire has decreased dramatically over the past few decades. In the 1970s, the average time from the start of a house fire to flashover was approximately 17 minutes. Today, that time has been reduced to as little as 3 to 4 minutes. The reason is that modern homes are filled with synthetic materials, polyester fabrics, polyurethane foam cushions, plastic electronics, laminated wood products that burn far faster and far hotter than the natural materials used in older homes. A sofa made with polyurethane foam can be fully engulfed in flames within about 3 minutes. The same style of sofa made with natural cotton and wool stuffing, as was common decades ago, would take much longer to reach the same level of burning. Modern furnishings are essentially fast-burning fuel, and they produce thick, toxic smoke that can incapacitate a person in just a few breaths. This is why fire safety experts stress the importance of working smoke detectors and a practiced escape plan. In a modern house fire, you may have less than 3 minutes to get out alive. There is no time to search for belongings, no time to get dressed, no time to investigate the source of the smoke. When the alarm sounds, you go. Immediately. Let us move on to something truly astonishing, the temperature of fire. Most people have a vague sense that fire is hot, but few appreciate just how extreme those temperatures can be or how widely they vary. A match flame burns at roughly 600 to 800 degrees Celsius. A wood fire in a fireplace reaches about 600 to 1000 degrees Celsius. A propane torch can produce temperatures of about 1995 degrees Celsius. An oxyacetylene welding torch reaches approximately 3500 degrees Celsius, hot enough to cut through steel like butter. And a plasma arc torch can achieve temperatures of 28,000 degrees Celsius, which is roughly 5 times the temperature of the surface of the sun. At the other end of the scale, a smoldering cigarette burns at only about 400 to 700 degrees Celsius at its tip, and a smoldering peat fire can sustain combustion at temperatures as low as 200 to 300 degrees Celsius. Fire exists across an enormous temperature spectrum, from gentle smoldering to the hellish heat of industrial torches that can vaporize metal. The color of a flame is directly related to its temperature, and this relationship follows a predictable pattern. Cooler flames tend to be red or deep orange. As the temperature increases, the color shifts to bright orange, then yellow, then white, and finally to blue. The hottest part of a Bunsen burner flame, for example, is the nearly invisible blue cone at its center, which can reach temperatures of about 1500 degrees Celsius. The yellow safety flame of the same burner, which looks more dramatic, is actually significantly cooler. This is the opposite of what most people intuitively believe. We tend to associate red and orange with heat and blue with cold, but in the world of fire, blue means the hottest and red means the coolest. Steelworkers and blacksmiths have known this for centuries. They judge the temperature of heated metal by its color. Dull red means about 500 degrees Celsius. Cherry red is about 750 degrees. Bright yellow is around 1000 degrees, and white heat indicates temperatures above 1200 degrees. This color-temperature relationship is governed by the physics of black body radiation and has been understood scientifically since the 19th century. Here is a fire fact that sounds impossible but is absolutely true. Water under certain conditions can actually make a fire worse. If you throw water on a grease fire, the kind that starts in a kitchen when cooking oil overheats, the result can be catastrophic. Cooking oil burns at temperatures well above the boiling point of water. When water hits the superheated oil, it instantly flashes into steam, expanding to roughly 1,700 times its original volume in a fraction of a second. This explosive expansion of steam launches burning oil droplets into the air in a massive fireball that can reach the ceiling and spread the fire to curtains, cabinets, and anything else nearby. A small grease fire that could have been smothered with a pot lid can be transformed into a kitchen-destroying blaze by a single cup of water. This is why fire safety training consistently emphasizes that you should never, ever throw water on a grease fire. Instead, you should smother it by covering the pot or pan with a lid. Use a fire extinguisher rated for grease fires, or in extreme cases, use baking soda, never flour, which is itself combustible, to smother the flames. Speaking of flour, here is another counterintuitive fire fact. Many common, seemingly harmless substances are explosively flammable when they are dispersed in the air as fine particles. Flour, sugar, sawdust, coal dust, grain dust, and even powdered milk can explode violently when suspended in air and ignited. These are called dust explosions, and they are one of the most underappreciated fire hazards in industrial settings. A dust explosion occurs when fine combustible particles are dispersed in the air at the right concentration, mixed with oxygen, and exposed to an ignition source. The enormous surface area of the dispersed particles allows them to burn almost instantaneously, producing a rapid pressure wave that can demolish buildings. Grain elevators, flour mills, sugar refineries, and woodworking shops are all vulnerable to dust explosions, and numerous deadly incidents have occurred throughout history. One of the worst was the Washburn Mill explosion in Minneapolis in 1878, which destroyed the largest flour mill in the world at the time, killed 18 workers, and leveled several adjacent buildings. The cause was flour dust suspended in the air inside the mill, ignited by a spark. The explosion was so powerful that it was heard miles away. Modern industrial facilities use ventilation systems, dust suppression measures, and explosion-proof equipment to minimize the risk, but dust explosions remain a serious concern in many industries. Now let us discuss a type of fire that exists at a completely different scale, the fires of the sun. The sun is often described as a giant ball of fire, but this is not technically accurate. The sun does not burn in the way that a campfire or a candle burns. There is no combustion happening on the sun because combustion requires a chemical reaction between fuel and oxygen, and the processes powering the sun are not chemical, they are nuclear. The sun is powered by nuclear fusion, a process in which hydrogen atoms are forced together under enormous pressure and temperature to form helium atoms. This process releases staggering amounts of energy, far more than any chemical reaction could ever produce. The temperature at the core of the sun is approximately 15 million degrees Celsius, and the core produces energy at a rate equivalent to detonating approximately 100 billion hydrogen bombs every single second. If the sun were actually burning, consuming its hydrogen through chemical combustion like a giant campfire, it would have burned out in about 5,000 years. The fact that it has been shining for 4.6 billion years is proof that something far more powerful than fire is at work. So while the sun looks like fire and we commonly describe it using fire imagery, it is actually something much more extreme. But there is real fire on other planets, or at least conditions that could support it. On Titan, the largest moon of Saturn, there are lakes and rivers of liquid methane and ethane on the surface. Methane is, of course, a highly flammable gas here on Earth, but on Titan there is no free oxygen in the atmosphere, so the methane cannot burn. However, if oxygen were somehow introduced, the entire landscape could theoretically ignite. Scientists have speculated about what fire would look like on Titan and have concluded that, given the moon's low gravity and dense atmosphere, flames would be taller, slower, and cooler than they are on Earth. The chemistry of extraterrestrial fire is a genuine field of study, and as we explore more of the solar system, understanding how fire behaves in different atmospheres and gravities will become increasingly important. Let us return to Earth for a moment and talk about one of the most remarkable materials ever created to resist fire, asbestos. Asbestos is a naturally occurring mineral fiber that is almost completely resistant to heat, flame, and chemical degradation. The ancient Greeks knew about asbestos and gave it its name, which means inextinguishable. According to legend, the Roman Emperor Charlemagne impressed his guests by throwing a tablecloth made of asbestos into a fire and then pulling it out unharmed. For centuries, asbestos was considered a miracle material. It was woven into fireproof clothing, used to insulate buildings and industrial equipment, mixed into brake pads and roofing shingles, and incorporated into thousands of consumer products. Its resistance to fire seemed like a gift from nature, but the miracle came with a devastating cost. Asbestos fibers, when inhaled, become lodged in the lungs and cannot be broken down or expelled by the body. Over time, they cause scarring, inflammation, and eventually, a rare and aggressive form of cancer called mesothelioma. The health effects of asbestos exposure were recognized as early as the beginning of the 20th century, but the asbestos industry suppressed and denied the evidence for decades. Millions of workers were exposed to asbestos without adequate protection, and hundreds of thousands have died from asbestos-related diseases. Today, asbestos is banned or heavily regulated in most developed countries, but it remains a legacy hazard in older buildings and a continuing health crisis in parts of the developing world. The story of asbestos is a stark reminder that our relationship with fire and with the materials we create to control it is never simple. Let us talk about fire and warfare, because the military use of fire is as old as warfare itself. One of the most famous and mysterious fire weapons in history is Greek fire, a terrifying incendiary weapon used by the Byzantine Empire beginning in the 7th century. Greek fire was a liquid substance that could be projected from tubes mounted on the prows of warships, similar to a modern flamethrower. What made Greek fire so devastating and so feared was that it burned on water. Conventional fires go out when doused with water, but Greek fire continued to burn even on the surface of the sea, clinging to ships and sailors and consuming them. Some historical accounts claim that water actually intensified the flames. The Byzantine navy used Greek fire to devastating effect, destroying enemy fleets and defending Constantinople from multiple sieges. The exact composition of Greek fire remains unknown to this day. The formula was a closely guarded state secret, known only to the Byzantine emperor and a small number of trusted craftsmen. When the Byzantine Empire fell, the secret was lost. Modern historians and chemists have proposed numerous possible formulations, including mixtures of naphtha, quicklime, sulfur, and various resins, but none has been definitively proven. Greek fire remains one of the great unsolved mysteries of military history. The use of fire in warfare continued to evolve over the centuries. In the 20th century, one of the most controversial fire weapons ever created was napalm. Napalm is a mixture of a gelling agent and a flammable liquid, usually gasoline. The gelling agent thickens the gasoline into a sticky, jelly-like substance that adheres to surfaces and burns at extremely high temperatures for an extended period. When napalm is ignited, it produces intense heat, thick smoke, and flames that are extremely difficult to extinguish. It sticks to skin, clothing, and structures, continuing to burn even as victims try to remove it. Napalm was used extensively during the Second World War, the Korean War, and the Vietnam War, causing massive destruction and horrific civilian casualties. The use of napalm and similar incendiary weapons against civilian populations was restricted by the United Nations Convention on Certain Conventional Weapons in 1980, but incendiary weapons have not been completely banned and continue to be used in some conflicts today. Now, let us explore one of the most counterintuitive facts about fire. Some materials can ignite spontaneously, without any external spark or flame. This phenomenon, called spontaneous combustion, occurs when a material generates heat internally through chemical reactions, usually slow oxidation, and the heat cannot escape fast enough to dissipate. The temperature builds up inside the material until it reaches its ignition point, and then it bursts into flames seemingly on its own. This is not a rare or theoretical phenomenon. It happens regularly and has been responsible for numerous fires and explosions throughout history. Oily rags are one of the most common culprits. Certain drying oils like linseed oil, tung oil, and even some cooking oils undergo an exothermic oxidation reaction as they dry. If rags soaked in these oils are piled together or crumpled in a confined space, the heat generated by the oxidation has no way to escape. The temperature rises and eventually the rags catch fire. This has caused countless fires in paint shops, furniture refinishing facilities, and homes where woodworking is done. Firefighters and safety professionals consistently warn that oily rags should be spread flat to dry or stored in airtight metal containers, never piled together. Haystacks are another classic example of spontaneous combustion. When hay is baled and stored while it is still slightly damp, microorganisms in the hay begin to decompose the plant material, generating heat as a byproduct. In a large haystack, this biological heat can accumulate to dangerous levels. Temperatures inside a poorly cured haystack can rise above 150 degrees Fahrenheit, and at around 300 degrees Fahrenheit, the hay begins to char and can eventually ignite. Farmers have lost entire barns to hay fires that seem to start from nowhere. The phenomenon was well known in agricultural communities for centuries before science could explain it, and it gave rise to legends and superstitions about cursed barns and vengeful spirits. There is also the long debated and deeply controversial topic of spontaneous human combustion, the idea that a human body can catch fire and burn without any external ignition source. Hundreds of cases have been reported over the centuries, typically involving individuals found severely or completely burned in rooms where the surrounding furniture and walls show little or no fire damage. The phenomenon was described in medical literature as early as the 17th century and has been a source of fascination and fear ever since. Charles Dickens even used spontaneous human combustion as a plot device in his novel Bleak House, in which a character named Crook is consumed by internal flames. Scientists have generally been skeptical of spontaneous human combustion, and most cases can be explained by conventional means: a dropped cigarette, a nearby heat source, or the wick effect, in which a small external flame ignites a person's clothing, and the body's own fat acts as fuel, slowly burning like a candle over many hours. The wick effect can produce the characteristic pattern of severe body burning with minimal damage to the surrounding room. While spontaneous human combustion makes for a compelling story, there is currently no scientific evidence that the human body can ignite without an external ignition source. Let us move on to something more practical and life-saving: the history of firefighting. The first organized firefighting force in recorded history was established in ancient Rome by a man named Marcus Licinius Crassus, who was one of the wealthiest men in the Roman Republic. Crassus created a private fire brigade of approximately 500 men, but his business model was, to put it mildly, morally questionable. When a building caught fire, Crassus and his men would rush to the scene. But instead of immediately fighting the fire, Crassus would negotiate with the building's owner, offering to buy the burning property at a fraction of its value. If the owner agreed, and with their property actively on fire, they often did, Crassus would purchase the building and then order his men to extinguish the flames. He would then repair the building and either sell it or rent it out at a profit. If the owner refused to sell, Crassus would simply let the building burn. Through this ruthless strategy, Crassus amassed an enormous real estate empire and became one of the richest men in Roman history. It was not until the Emperor Augustus established the Vigils, a publicly funded fire brigade and night watch of about 7,000 men, that Rome had a fire service that actually prioritized saving lives and property over making money. The development of firefighting technology has been a long and fascinating journey. For most of human history, the primary tools for fighting fire were buckets of water, hand-operated pumps, and controlled demolition, pulling down buildings in the path of a fire to create a gap that the flames could not cross. The first fire engines were essentially hand-pumped water squirters mounted on carts, developed in the 17th and 18th centuries. These early engines required teams of men to operate the pumps and could only deliver a modest stream of water. Steam-powered fire engines appeared in the mid-19th century, dramatically increasing the volume and pressure of water that could be directed at a fire. Motorized fire engines replaced horse-drawn steam engines in the early 20th century, and modern fire trucks now carry a vast array of equipment: hoses, ladders, breathing apparatus, thermal imaging cameras, hydraulic rescue tools, foam generators, and sophisticated communication systems. The modern firefighter is equipped with technology that would have seemed like science fiction to the bucket brigades of centuries past. One of the most important advances in fire safety has nothing to do with firefighting at all. It is the smoke detector. The first residential smoke detector was introduced in the late 1960s and early 1970s, and its impact on fire deaths has been staggering. Before smoke detectors became widespread, the annual fire death rate was dramatically higher than it is today. Studies have shown that a working smoke detector reduces the risk of dying in a home fire by approximately 50%. The reason is simple. Most fatal house fires occur at night when people are asleep. Smoke, not flames, is the primary killer in most house fires. Toxic gases in the smoke, particularly carbon monoxide and hydrogen cyanide, can render a sleeping person unconscious in just a few breaths, long before the flames reach them. A smoke detector alerts people early while there is still time to escape. Despite their proven effectiveness, a disturbing number of fire deaths still occur in homes without working smoke detectors, often because the batteries have been removed or have died. Fire safety experts recommend testing smoke detectors monthly and replacing the batteries at least once a year. Now, here is a fact that reveals just how powerful fire can be as a force of destruction. The Great Fire of London, which burned from September 2 to September 6, 1666, destroyed approximately 13,200 houses, 87 churches, and most of the buildings of the City of London. The fire started in a bakery on Pudding Lane and spread rapidly through the densely packed, timber-framed buildings of the medieval city. The strong easterly wind fanned the flames, and the fire burned for 4 days before it was brought under control, largely through the creation of fire breaks demolishing buildings to create gaps that the fire could not cross. Amazingly, despite the enormous scale of the destruction, the official death toll was recorded as only 6 people, although modern historians believe the actual number was significantly higher, as many deaths among the poor and homeless may not have been recorded. The Great Fire transformed London. In the rebuilding that followed, new building codes required the use of brick and stone instead of timber, streets were widened, and fire safety measures were greatly improved. The fire also led to the establishment of organized fire insurance companies and the creation of the first professional fire brigades in the city's history. Let us talk about an element that has a truly bizarre relationship with fire: oxygen. We have already discussed how oxygen is essential for combustion, but what happens when you increase the oxygen concentration beyond the normal atmospheric level of about 21%? The results are dramatic and dangerous. In a pure oxygen environment, or even in an environment with moderately elevated oxygen levels, materials that are normally difficult to ignite become dangerously flammable. Steel wool, which will barely smolder in normal air, burns vigorously in pure oxygen. Fabrics that would resist ignition in a normal atmosphere burst into flame from the slightest spark in an oxygen-enriched environment. Even materials that are considered non-flammable under normal conditions, like certain metals, can burn in pure oxygen. This was tragically demonstrated in 1967 during a routine test of the Apollo 1 spacecraft. The cabin of the command module was filled with pure oxygen at a pressure slightly above normal atmospheric pressure. During the test, a spark, probably from a damaged wire, ignited materials inside the cabin. In the pure oxygen environment, the fire spread with incredible speed and ferocity. The 3 astronauts, Gus Grissom, Ed White, and Roger Chaffee, were killed within seconds. The disaster led to major redesigns of the spacecraft, including the replacement of the pure oxygen atmosphere with a less flammable oxygen-nitrogen mixture and the use of fire-resistant materials throughout the cabin. Here is another oxygen-related fact. The Earth's atmosphere has not always contained 21% oxygen. During the Carboniferous period, roughly 300 to 350 million years ago, atmospheric oxygen levels reached as high as 35%, significantly higher than today. This elevated oxygen had dramatic effects on life and on fire. Insects, which breathed through a passive diffusion system called tracheae, grew to enormous sizes in the oxygen-rich atmosphere. Dragonflies had wingspans of over 2 feet, millipedes grew to lengths of over 6 feet, and fire burned with far greater intensity and ferocity than it does today. Experiments have shown that at 35% oxygen, even damp wood and green vegetation can burn readily. Wildfires during the Carboniferous must have been extraordinarily intense, burning hotter, faster, and more completely than any modern wildfire. The abundance of fossilized charcoal from this period confirms that fire was a dominant force in shaping carboniferous ecosystems. Some scientists believe that the elevated fire activity actually helped regulate atmospheric oxygen levels. More fire consumed more organic material, reducing the production of oxygen from photosynthesis and the accumulation of unburned carbon, creating a negative feedback loop that prevented oxygen levels from rising to even more extreme concentrations. Let us talk about one more surprising fact before we close out this section. Many people believe that the primary danger in a fire is the heat of the flames, but this is not true. In most fire deaths, the actual killer is smoke inhalation, not burns. Smoke is a complex mixture of gases, particulate matter, and aerosolized chemicals, many of which are extremely toxic. The primary lethal components of smoke are carbon monoxide, which binds to hemoglobin in the blood far more readily than oxygen, effectively suffocating the body's cells even when the victim is still breathing, and hydrogen cyanide, which disrupts the cellular processes that allow cells to use oxygen, causing rapid cellular asphyxiation. In a typical house fire, the concentration of these toxic gases can reach lethal levels within minutes. A person who breathes in large amounts of carbon monoxide becomes confused, disoriented, and eventually unconscious, often before they are even aware that they are in danger. This is why fire safety experts advise people to stay low to the ground when escaping a fire. Smoke and hot gases rise, so the air near the floor is typically cooler, cleaner, and more breathable. Crawling on your hands and knees below the smoke layer can mean the difference between life and death. Smoke also reduces visibility to near zero. In a room filled with thick smoke, you may not be able to see your own hand in front of your face. This disorientation is one of the most dangerous aspects of a house fire. People become lost in their own homes, unable to find doors, windows, or exits that they have used thousands of times before. Firefighters train extensively for these conditions, learning to navigate by touch, by memory, and by following walls, because vision is completely useless in dense smoke. The combination of toxic gases, extreme heat, and zero visibility makes structural fires one of the most hazardous environments that any human being can enter, and it is a testament to the courage and training of firefighters that they enter these environments voluntarily, day after day, to save the lives of strangers. This brings us to a sobering but important fact about the human relationship with fire. Despite all of our technology, all of our knowledge, and all of our safety systems, fire continues to kill and injure people at an alarming rate. Globally, fire causes hundreds of thousands of deaths every year and millions of injuries. House fires, vehicle fires, industrial fires, and wildfires claim lives on every continent and in every season. The vast majority of these deaths are preventable. They are caused by unattended cooking, discarded cigarettes, faulty wiring, overloaded electrical circuits, children playing with matches, improperly stored flammable materials, and the absence of working smoke detectors. Fire does not discriminate. It does not care about wealth, status, or intelligence. It obeys only the laws of chemistry and physics, and it will consume anything and anyone in its path if given the opportunity. The best defense against fire is not bravery or strength. It is knowledge, preparation, and respect for the extraordinary power of this ancient force. We have covered an enormous amount of ground in this first part of our journey through the world of fire. We have explored the chemistry of a candle flame, the physics of fire in zero gravity, the biology of fire-adapted plants, the history of human fire use, the terrifying power of wildfires and fire tornadoes, the hidden danger of underground coal fires, the deadly dynamics of structural fires, the astonishing temperatures that fire can reach, the explosive potential of common dust, the nuclear fires of the sun, the mystery of Greek fire, the science of spontaneous combustion, the evolution of firefighting, and the toxic lethality of smoke. And yet, we have only scratched the surface. In the next part of this documentary, we will go even deeper. We will explore the role of fire in religious rituals and mythology across cultures. We will examine the chemistry of the most powerful explosives ever created. We will investigate the strange phenomenon of fires that burn in colors you have never seen. We will learn how fire has been used in medicine, in art, in architecture, and in the transformation of raw materials into the tools and technologies that built civilization. We will visit the hottest fires ever produced by human beings and the coldest flames that science has discovered. We will examine how climate change is altering the behavior of wildfires and what that means for the future of life on Earth. Fire is not just a chemical reaction. It is a force that has shaped the course of evolution, the rise and fall of civilizations, the development of technology, and the very way we think about the world. It is a force of creation and destruction, of warmth and terror, of beauty and devastation. It is one of the oldest forces in the universe, and it remains one of the least understood by the general public. By the end of this documentary, you will see fire in a completely new way. You will understand its science, respect its power, and appreciate its role in making the world and making us what we are today. Fire has always been with us, and no matter how advanced our technology becomes, fire will always be with us. The question is not whether we will encounter fire, but whether we will be prepared when we do. Welcome back. In the first part of this documentary, we journeyed through the science of combustion, the evolutionary history of fire, and the terrifying power of wildfires, structural fires, and underground infernos. We explored how fire shaped the human body and the human mind, how it behaves in the weightlessness of space, and how smoke, not flame, is the true killer in most fire deaths. But we have only told half the story. There is so much more to discover about this ancient, elemental force. In this second part, we will go deeper, wider, and further than before. We will travel from the volcanic forges of the ancient earth to the controlled infernos of modern industry, from sacred temple flames that have burned for centuries to the invisible chemical fires that rage inside your own body at this very moment. We will uncover secrets that will astonish you, facts that will unsettle you, and truths that will forever change the way you look at the simple act of striking a match. Let us begin with something that connects fire to the deepest layers of human belief and spirituality, because fire is not just a physical phenomenon. It is one of the most powerful symbols in human culture, and it has been at the center of religious worship for thousands of years. In the ancient Zoroastrian religion, which originated in Persia more than 3,000 years ago, fire is considered the supreme symbol of truth, righteousness, and divine presence. Zoroastrian temples maintain sacred fires that are tended by priests and are never allowed to go out. Some of these fires have been burning continuously for over 1,000 years. The Adash Barem, the highest grade of sacred fire in Zoroastrianism, requires the combination of 16 different types of fire, including fire from lightning, fire from a funeral pyre, fire from a goldsmith's furnace, and fire from a baker's oven, among others. The process of consecrating an Adash Barem takes years and involves elaborate purification rituals. Once consecrated, the fire is treated as a living embodiment of the divine and is fed 5 times a day with sandalwood and prayers. Zoroastrians do not worship fire itself. They worship the divine truth that fire represents, but the centrality of fire to their faith is unmatched by any other major religion. The fact that these temple fires have been maintained continuously for centuries, through wars, invasions, and natural disasters, is a testament to the profound reverence that humans have held for fire since the earliest days of civilization. Fire occupies a sacred place in Hinduism as well. The Hindu fire god Agni is one of the most important deities in the Vedic tradition and is mentioned more times in the ancient Hindu scriptures than almost any other god. Agni is considered the messenger between the human world and the divine world because fire carries offerings upward to the gods in the form of smoke. The Hindu fire ritual known as the yajna or havan involves the lighting of a sacred fire and the offering of ghee, grains, herbs, and other materials into the flames while chanting mantras. These rituals have been performed continuously for over 3,000 years and remain a central part of Hindu worship today. In Hindu wedding ceremonies, the couple walks around a sacred fire 7 times, and the fire is considered the primary witness to the marriage vows. Without fire, the marriage is not considered complete. Fire in the Hindu worldview is not merely a tool or a force of nature. It is a divine being, a purifier, a transformer, and a bridge between the mortal and the eternal. The ancient Greeks incorporated fire into one of their most enduring myths, the story of Prometheus. According to the myth, Prometheus was a titan who stole fire from the gods on Mount Olympus and gave it to humanity. Before this gift, humans lived in darkness and cold, unable to cook food, forge tools, or protect themselves from the night. Prometheus's gift of fire transformed the human condition, but it came at a terrible price. Zeus, the king of the gods, was furious at the theft and punished Prometheus by chaining him to a rock, where an eagle ate his liver every day, only for it to regenerate each night, condemning him to an eternity of agony. The myth of Prometheus is one of the oldest and most profound stories about the relationship between humans and fire. It captures something deeply true, that fire is both a gift and a danger, a source of power and a source of suffering. Every civilization that has mastered fire has also been burned by it, and the myth of Prometheus reminds us that the power to create is always accompanied by the power to destroy. The Olympic flame, which has become one of the most recognizable symbols in the modern world, traces its origins directly back to the sacred fires of ancient Greece. In the ancient Olympic Games, a flame was kept burning throughout the duration of the competition in honor of the goddess Hestia, the guardian of the hearth. The modern tradition of the Olympic flame was introduced at the 1928 Games in Amsterdam, and the torch relay, in which a flame is carried by a series of runners from Olympia, Greece, to the host city, was first implemented at the 1936 Berlin Games. The flame is lit in a ceremony at the ancient site of Olympia using a parabolic mirror that focuses the rays of the sun. No matches, no lighters, no artificial means, only the concentrated power of sunlight. If the flame goes out during the relay, it must be ray-lit from a backup flame that was itself lit from the original solar ceremony. The Olympic flame is meant to symbolize the continuity between the ancient and modern games and the enduring ideals of peace, unity, and human achievement. It is a beautiful example of how fire continues to carry symbolic power in the modern world. Now let us shift from the spiritual to the practical and talk about one of the most important ways that fire has shaped human civilization, metallurgy. The ability to extract metals from ore and shape them into tools, weapons, and structures is one of the defining achievements of human history, and none of it would have been possible without fire. The earliest metalworking dates to approximately 7,000 years ago, when people in the ancient Near East discovered that certain colorful rocks, when heated in a fire to sufficiently high temperatures, would release a shiny, malleable substance, copper. This was the birth of the Copper Age, and it marked the beginning of humanity's long and transformative relationship with metals. But copper, while useful, is relatively soft. The next great leap came with the discovery that mixing copper with tin produces an alloy called bronze, which is significantly harder, more durable, and better suited for tools and weapons. The Bronze Age, which began around 3300 BCE, saw the development of sophisticated smelting furnaces that could reach temperatures of over 1000 degrees Celsius, hot enough to melt copper and tin and allow them to be combined. These furnaces were marvels of ancient engineering, using carefully designed air channels and bellows to increase the oxygen supply and raise the temperature of the fire. The development of bronze tools and weapons transformed warfare, agriculture, construction, and trade, and it was fire that made all of it possible. The next revolution came with iron. Iron ore is far more abundant than copper or tin, but it requires much higher temperatures to smelt, approximately 1538 degrees Celsius to melt pure iron, although early smelting techniques could produce workable iron at somewhat lower temperatures by creating a spongy mass called a bloom. The development of furnaces capable of reaching these extreme temperatures was one of the great technical achievements of the ancient world. The Iron Age, which began around 1200 BCE, ushered in a new era of stronger tools, more effective weapons, and more resilient structures. Iron plows could break harder soils, opening up new land for agriculture. Iron swords and armor changed the nature of warfare. Iron nails and fittings made new forms of construction possible. And all of it, every iron tool, every iron weapon, every iron nail was born in fire. The mastery of fire in metallurgy reached its pinnacle with the development of steel, an alloy of iron and carbon. Steel is harder, stronger, and more flexible than pure iron, and its properties can be precisely controlled by varying the carbon content and the heat treatment. The process of making steel requires not just high temperatures but precise temperature control, heating the metal to exactly the right temperature, holding it there for exactly the right duration, and then cooling it at exactly the right rate. Different cooling methods, quenching in water, quenching in oil, or slow air cooling, produce steels with very different properties. A rapidly quenched steel is extremely hard but brittle. A slowly cooled steel is softer but more flexible. The ancient Japanese swordsmiths who created the legendary katana understood these principles intuitively, even without the benefit of modern metallurgical science. They would heat the blade, fold the steel, hammer it, heat it again, and repeat the process dozens or even hundreds of times, creating a blade with a layered internal structure that combined the hardness of high-carbon steel at the cutting edge with the flexibility of low-carbon steel at the spine. The result was a weapon of extraordinary beauty and effectiveness, a masterpiece born from fire. Fire also gave us glass, one of the most versatile and important materials in human history. The earliest known glass objects date to approximately 3500 BCE in ancient Mesopotamia and Egypt. Glass is made by heating silica, usually in the form of sand, to temperatures above 1700 degrees Celsius, at which point it melts and becomes a viscous liquid. When this liquid cools, it does not crystallize like most materials. Instead, it forms an amorphous solid, a material that is technically neither a true solid nor a liquid, but an intermediate state with the rigidity of a solid and the disordered molecular structure of a liquid. Ancient glassmakers discovered that adding certain materials to the silica, soda ash to lower the melting point, lime to improve durability, and various metal oxides to produce colors, could create an extraordinary range of beautiful, functional objects. The development of glass blowing around the 1st century BCE was a major breakthrough, allowing artisans to create hollow vessels, bottles, and decorative objects with a speed and variety that had never before been possible. Today, glass is everywhere in windows, lenses, fiber optic cables, laboratory equipment, smartphone screens, and countless other applications. Every piece of glass you have ever seen began as sand that was transformed by the power of fire. Ceramics are another material that owes its existence entirely to fire. Pottery, clay shaped by human hands and then hardened in a kiln, is one of the oldest human technologies. The earliest known ceramic objects, small figurines found in what is now the Czech Republic, date to approximately 29,000 years ago, making them far older than any known pottery vessel. The oldest known pottery vessels, used for cooking and storage, date to approximately 20,000 years ago in East Asia. The process of firing clay involves heating it to temperatures between 600 and 1,400 degrees Celsius, depending on the type of clay and the desired result. At these temperatures, the water molecules trapped between the clay particles are driven off, and the silicate minerals in the clay undergo chemical changes that permanently harden the material. A fired pot is fundamentally different from an unfired one. It is harder, more durable, and waterproof. The invention of pottery revolutionized human life. It allowed people to store food and water, cook stews and soups, ferment beverages, and transport goods. And it was fire-controlled, sustained, carefully managed fire that made it all possible. Let us now talk about one of the most dramatic and visually stunning applications of fireworks. We mentioned fireworks briefly earlier in relation to flame colors, but the history and science of fireworks deserve a much closer look. The origin of fireworks traces back to ancient China, where alchemists experimenting with mixtures of sulfur, charcoal, and potassium nitrate accidentally discovered gunpowder, also known as black powder, sometime around the 9th century. According to legend, the earliest firecrackers were created by filling bamboo tubes with this explosive mixture and throwing them into a fire, producing a loud bang that was believed to frighten evil spirits. Over time, Chinese pyrotechnicians developed increasingly sophisticated devices, rockets that soared into the sky, fountains of colored sparks, and aerial shells that burst into patterns of light high above the ground. The science behind a modern firework shell is remarkably complex. The shell consists of a lifting charge that propels it into the air, a time delay fuse that ignites the burst charge at the right altitude, and carefully arranged clusters of small pellets called stars. Each star is a compressed mixture of an oxidizer, a fuel, a color-producing metal salt, and a binder. The arrangement of the stars within the shell determines the shape of the burst: a ring, a palm tree, a smiley face, a cascading willow. The timing of the fuse determines the altitude of the burst, and the chemical composition of each star determines its color, brightness, and duration. Creating a firework display that is both beautiful and safe requires an extraordinary combination of chemistry, engineering, and artistry. A single large firework shell can contain dozens of individual stars, each one a precisely engineered combustion device, and a major fireworks display can involve thousands of shells fired in carefully choreographed sequences synchronized to music. It is one of the most spectacular applications of fire science in the world. Now here's something truly unexpected about fire. It exists inside your body right now. Not literal fire, of course, but the same fundamental chemical process that drives combustion, oxidation, is happening inside every cell of your body at this very moment. Cellular respiration, the process by which your cells extract energy from food, is essentially a very slow, very controlled form of burning. In cellular respiration, glucose molecules from the food you eat are combined with oxygen from the air you breathe, and the chemical bonds are broken to release energy. The products of this reaction are carbon dioxide and water, exactly the same products produced by burning wood or any other organic material. The chemical equation for cellular respiration is virtually identical to the chemical equation for combustion. The difference is that in your body, the process is regulated by enzymes and occurs in tiny, controlled steps, releasing energy gradually in a form that your cells can use, rather than all at once in a burst of heat and light. But at the molecular level, the chemistry is the same. You are, in the most literal biochemical sense, burning your food to stay alive. Your body temperature, approximately 98.6 degrees Fahrenheit, is maintained by the heat released from this continuous internal combustion. You are a slow-burning fire wrapped in skin. Speaking of body temperature, let us talk about something that seems to defy the laws of physics: fire walking. In many cultures around the world, people walk barefoot across beds of hot coals as part of religious ceremonies, spiritual rituals, or demonstrations of faith. The coals can have surface temperatures of 500 to 600 degrees Celsius, which is more than hot enough to cause severe burns. And yet experienced fire walkers routinely cross these beds without injury. How is this possible? The answer lies in the physics of heat transfer. There are three ways that heat can be transferred: conduction, convection, and radiation. In fire walking, the relevant mechanism is conduction, the transfer of heat through direct contact between the foot and the coal. Several factors protect the fire walker. First, charcoal is a very poor conductor of heat. Despite its high temperature, it transfers heat to the foot slowly, much more slowly than, say, a metal surface at the same temperature. If you touched a piece of metal at 500 degrees Celsius, you would be burned almost instantly because metal is an excellent conductor, but charcoal transfers its heat much less efficiently. Second, the contact time is very brief. Fire walkers keep moving, spending only a fraction of a second in contact with any individual coal. Third, the moisture on the surface of the foot, from sweat or from walking on damp grass before the walk, creates a thin layer of steam between the foot and the coal, a phenomenon related to what physicists call the Leidenfrost effect. This steam layer acts as a brief insulating barrier. However, it is important to note that fire walking is not without risk. Walkers who move too slowly, who stop on the coals, or who encounter a coal with a particularly hot surface or embedded metal debris can and do suffer serious burns. Fire walking is not magic, it is physics, but it is physics that must be respected. Let us now explore one of the most important and least appreciated aspects of fire in modern life, the role of fire in generating electricity. Even in the 21st century, a substantial portion of the world's electricity is produced by burning things. Coal-fired power plants, natural gas power plants, and oil-burning generators all work on the same basic principle. Fuel is burned to produce heat. The heat is used to boil water and produce steam. The steam drives a turbine, and the turbine spins a generator that produces electricity. It is, at its core, a fire-powered system. Despite the rapid growth of renewable energy sources like solar and wind, fossil fuel combustion still accounts for a significant majority of global electricity generation. Every time you flip a light switch, charge your phone, or run your air conditioner, there is a good chance that somewhere a fire is burning to make that possible. Our modern technological civilization, with all of its digital sophistication and wireless connectivity, is still fundamentally built on the same force that our ancestors huddled around in caves hundreds of thousands of years ago. Nuclear power, while not involving fire in the traditional sense, deserves mention here because it produces heat through a process that, like the sun, goes far beyond ordinary combustion. In a nuclear reactor, the fission of uranium or plutonium atoms releases enormous amounts of heat, which is then used to boil water and drive turbines, just like in a conventional power plant. The heat generated by nuclear fission is millions of times more intense per unit of fuel than the heat generated by burning coal or gas. A single fuel pellet of enriched uranium, about the size of a pencil eraser, contains as much energy as 17,000 cubic feet of natural gas, 1,780 pounds of coal, or 149 gallons of oil. Nuclear energy is in a sense the ultimate fire, a controlled release of the energy locked inside the atom itself. Now let us discuss a topic that has become increasingly urgent in recent years, the relationship between climate change and wildfire. The science is clear and deeply concerning. As global temperatures rise due to the accumulation of greenhouse gases in the atmosphere, wildfire seasons are becoming longer, more intense, and more destructive. Higher temperatures dry out vegetation more quickly and more thoroughly, creating larger volumes of dry, burnable fuel. Earlier snowmelt reduces soil moisture, extending the period during which landscapes are vulnerable to ignition. Hotter, drier conditions create lower humidity, which accelerates the rate at which fires spread, and changes in wind patterns driven by shifts in atmospheric circulation are bringing stronger, more unpredictable winds to fire-prone regions. The results have been devastating. In recent years, record-breaking wildfire seasons have been observed on nearly every continent. Fires have burned through millions of acres of forest, destroyed thousands of homes, killed hundreds of people, and blanketed entire regions in choking, hazardous smoke. The smoke from large wildfires does not stay local. It can travel thousands of miles, crossing oceans and continents, degrading air quality in cities far removed from the actual flames. Wildfire smoke contains fine particulate matter, carbon monoxide, volatile organic compounds, and other toxic substances that cause respiratory illness, cardiovascular problems, and premature death. Studies have shown that exposure to wildfire smoke, even at relatively low concentrations, is associated with increased rates of asthma attacks, heart attacks, strokes, and hospitalizations. As wildfires grow larger and more frequent, the public health impact of wildfire smoke is becoming a major concern for communities that may be hundreds or even thousands of miles from the nearest fire. Climate scientists project that these trends will continue and accelerate in the coming decades unless greenhouse gas emissions are drastically reduced. Some models suggest that the area burned by wildfires globally could double or even triple by the end of the century under high-emission scenarios. Fire-adapted ecosystems that have coexisted with periodic burning for millennia are now experiencing fires of a frequency and intensity that exceeds their ability to recover. Forests that once regenerated quickly after fire are being converted to shrublands or grasslands because the fires are returning so frequently that young trees cannot grow to maturity before the next blaze arrives. In some regions, fire is fundamentally transforming the landscape, replacing forests with entirely different ecosystems. The relationship between fire and climate is a feedback loop. Fires release enormous amounts of carbon dioxide stored in vegetation and soil, which contributes to further warming, which drives more fires, which release more carbon. Breaking this cycle is one of the defining challenges of our time. Let us now turn to a fascinating and little-known topic, fire investigation. When a fire occurs, particularly a suspicious fire, specially trained investigators are called in to determine how the fire started, where it originated, and whether it was set intentionally. Fire investigation is part science, part detective work, and part art. The investigator must read the physical evidence left behind by the fire, burn patterns on walls and floors, the depth of charring on wooden surfaces, the behavior of melted metals and glass, the direction of smoke staining, and the location and condition of potential ignition sources. By carefully examining these clues, the investigator can reconstruct the fire's behavior in reverse, tracing the path of the flames back to the point of origin. One of the most important tools in fire investigation is the analysis of burn patterns. Fire burns upward and outward from its point of origin, creating a characteristic V-shaped pattern on vertical surfaces. The point of the V indicates the area where the fire was most intense, which often corresponds to the location of the ignition source. Deep charring on the floor, known as pour patterns, can indicate the use of an accelerant, a flammable liquid like gasoline that is poured on the floor to spread the fire quickly and ensure that it burns hot enough to destroy evidence. Investigators collect samples of debris from areas suspected of containing accelerants and send them to laboratories for chemical analysis using gas chromatography and mass spectrometry. These techniques can detect trace amounts of flammable liquids even after they have been partially consumed by the fire. Arson, the deliberate setting of a fire, is one of the most difficult crimes to solve because fire itself destroys much of the evidence. Arsonists know this, and many set fires specifically to cover up other crimes, such as burglary, fraud, or murder. Insurance fraud is one of the most common motives for arson. A business owner facing bankruptcy might set fire to their own property to collect the insurance payout. A homeowner who cannot sell their house might burn it down to recover the mortgage value. Detecting these crimes requires a combination of fire science and traditional detective work, examining the owner's financial records, interviewing witnesses, reviewing security camera footage, and looking for physical evidence of intent, such as disabled smoke detectors, removed valuables, or multiple points of origin. Here is a fact about arson that is both surprising and troubling. Studies have shown that a significant percentage of arson fires are set by firefighters themselves. This seems paradoxical. The very people trained to fight fire are sometimes the ones starting them. The phenomenon, while rare in absolute terms, has been documented extensively. The motivations vary. Some firefighters set fires to create excitement, to be seen as heroes for responding to the blaze, to earn overtime pay, or because they suffer from impulse control disorders. Fire departments and law enforcement agencies are aware of this phenomenon and have developed investigative techniques specifically designed to detect firefighter arson, including monitoring response times, tracking patterns of fire locations, and conducting background checks on department personnel. It is a deeply disturbing aspect of the human relationship with fire, and a reminder that the fascination with flame can, in some individuals, cross the line from healthy respect to dangerous obsession. Speaking of obsession, let us discuss pyromania, a genuine psychiatric condition characterized by an irresistible impulse to set fires. Pyromania is classified as an impulse control disorder in the Diagnostic and Statistical Manual of Mental Disorders. True pyromaniacs set fires not for profit, not for revenge, not to cover up other crimes, but for the sheer psychological gratification of watching things burn. They experience increasing tension before setting a fire and intense relief or pleasure afterward. Pyromania is extremely rare, far rarer than most people believe. Studies suggest that fewer than 3% of arsonists meet the clinical criteria for pyromania. The vast majority of deliberately set fires are motivated by other factors: anger, revenge, financial gain, or the desire to conceal evidence. But pyromania, when it does occur, is a powerful illustration of the deep, almost primal hold that fire has on the human psyche. We are drawn to fire in ways that we do not fully understand, and for a small number of individuals, that attraction becomes an uncontrollable compulsion. Now let us explore something completely different, the extraordinary phenomenon known as St. Elmo's fire. Despite its name, St. Elmo's fire is not actually fire at all. It is a form of plasma discharge that occurs when a strong electric field ionizes the air molecules around a pointed object, such as the mast of a ship, the tip of an airplane wing, or the spire of a church steeple. The ionized air glows with a bright blue or violet light, creating an eerie, flickering luminescence that looks remarkably like a flame. Sailors have observed St. Elmo's fire for thousands of years, and it was traditionally considered either a good omen, a sign of protection from the patron saint of sailors, Saint Erasmus, also known as St. Elmo, or a warning of an approaching storm. In reality, St. Elmo's fire typically occurs during thunderstorms, when the electrical potential difference between the clouds and the ground is extremely high. The pointed objects on ships and buildings concentrate the electric field at their tips, causing the air to break down and glow. It is a beautiful and harmless phenomenon, but it has nothing to do with combustion. It is a reminder that not everything that looks like fire actually is fire. Another misleading fire-like phenomenon is the will-o'-the-wisp, also known as ignis fatuus, which is Latin for foolish fire. Will-o'-the-wisps are mysterious glowing lights that appear over swamps, marshes, and bogs, usually at night. They flicker and move, appearing to retreat when approached, which led to centuries of folklore about mischievous spirits luring unwary travelers into the bog to drown. The scientific explanation for will-o'-the-wisps is still debated, but the most widely accepted theory involves the spontaneous combustion of gases produced by the decomposition of organic matter in the swamp. As plant and animal material decays in the oxygen-poor environment of a bog, it produces methane and phosphine. Phosphine is a gas that can ignite spontaneously when it contacts the air, and its combustion can ignite the methane, producing a brief, flickering flame. The movement of the lights may be caused by air currents generated by the approach of the observer. While this explanation is plausible, it has been difficult to confirm experimentally, and will-o'-the-wisps remain one of the more elusive and enchanting fire phenomena in the natural world. Let us talk about one of the most extreme forms of fire ever created by human beings, the thermobaric weapon, sometimes called a vacuum bomb. A thermobaric weapon works in two stages. First, a small initial charge disperses a cloud of fine fuel, usually a metal powder or a flammable aerosol, over a wide area. Then a second charge ignites the fuel cloud, creating a massive fireball and an enormous pressure wave. The explosion is devastating for two reasons. First, the fireball is much larger than a conventional explosive blast because the fuel is distributed over a wide area before ignition. Second, the combustion consumes the oxygen in the surrounding air, creating a partial vacuum that follows the blast wave. This vacuum effect causes additional damage as the atmosphere rushes back in to fill the void. The combination of the blast wave, the fireball, and the vacuum makes thermobaric weapons extraordinarily destructive. particularly in enclosed spaces like buildings, tunnels, and caves. The pressure wave can collapse structures, and the vacuum can rupture lungs and other internal organs. These weapons represent one of the most terrifying applications of fire science in modern warfare. On a much less destructive but equally fascinating note, let us talk about the thermite reaction. Thermite is a mixture of a metal oxide, usually iron oxide, which is ordinary rust, and a more reactive metal powder, usually aluminum. When ignited, the aluminum reacts with the iron oxide in an extremely exothermic reaction, producing molten iron and aluminum oxide. The reaction reaches temperatures of approximately 2,500 degrees Celsius, which is hot enough to melt through steel, concrete, and virtually any other material. Thermite is used industrially for welding railroad tracks, a process called thermite welding, in which the molten iron produced by the thermite reaction fills the gap between two rail ends and fuses them together as it cools. It is a beautifully simple and elegant process. A crucible of thermite is placed above the gap, ignited, and within seconds, a stream of white-hot liquid iron pours down into the joint, creating a strong, seamless weld. The entire process takes less than a minute and requires no external power source, just the chemical energy stored in the thermite mixture. Now, let us discuss something that affects millions of people every year: the toxicity of fire smoke and the long-term health effects of smoke exposure. We discussed in the first part how carbon monoxide and hydrogen cyanide in smoke can kill within minutes. But even non-lethal smoke exposure can have serious long-term health consequences. Wildfire smoke contains fine particulate matter known as PM2.5, particles smaller than 2.5 micrometers in diameter, which is roughly 30 times smaller than the diameter of a human hair. These particles are small enough to penetrate deep into the lungs and even cross into the bloodstream. Once in the body, they trigger inflammation, oxidative stress, and immune responses that can damage the cardiovascular system, the respiratory system, and even the brain. Long-term exposure to fine particulate matter from smoke has been linked to increased rates of heart disease, stroke, chronic obstructive pulmonary disease, lung cancer, and cognitive decline. Firefighters who are exposed to smoke repeatedly over the course of their careers have significantly elevated rates of certain cancers, including lung cancer, bladder cancer, and mesothelioma, compared to the general population. The recognition of these occupational health risks has led to improvements in protective equipment for firefighters, including the use of self-contained breathing apparatus during fire suppression and the decontamination of gear after fire exposure. But the long-term health costs of smoke exposure remain a serious concern, both for professional firefighters and for the millions of ordinary people who breathe wildfire smoke during fire season. Let us now explore the fascinating world of fire retardants, materials and chemicals designed to slow or prevent the spread of fire. Fire retardants work by interfering with one or more elements of the fire tetrahedron. Some retardants release water when heated, cooling the material and diluting the flammable gases. Others release gases that displace oxygen, smothering the fire. Still others form a protective char layer on the surface of the material, insulating it from the heat and preventing the release of flammable vapors. Fire retardant chemicals are added to a vast range of consumer products: clothing, furniture, electronics, building materials, and even children's toys. They have undoubtedly prevented countless fires and saved many lives, but some fire retardants have come under scrutiny for their potential health and environmental effects. Certain classes of brominated and chlorinated fire retardants have been found to persist in the environment, accumulate in the tissues of animals and humans, and act as endocrine disruptors, chemicals that interfere with the body's hormonal systems. Some of these compounds have been detected in the blood and breast milk of people around the world, raising concerns about chronic low-level exposure. The challenge for fire safety scientists is to develop retardants that are effective at preventing fire without posing unacceptable risks to human health or the environment. It is a difficult balance, and it is a reminder that our efforts to control fire always involve trade-offs and unintended consequences. One of the most important fire safety innovations of the modern era is the automatic fire sprinkler system. Sprinkler systems were first developed in the 19th century for use in textile mills and other industrial buildings that were prone to devastating fires. The basic design is elegantly simple. A network of pipes is installed in the ceiling, with sprinkler heads at regular intervals. Each sprinkler head contains a heat-sensitive element, usually a glass bulb filled with a liquid that expands when heated or a fusible metal link that melts at a specific temperature. When a fire breaks out, the heat activates the nearest sprinkler head, which opens and releases a spray of water directly onto the fire. Contrary to popular belief, largely thanks to misleading portrayals in movies and television, a sprinkler activation does not cause all of the sprinklers in a building to go off simultaneously. Only the sprinklers in the immediate vicinity of the fire are activated. In most cases, a single sprinkler head is sufficient to control or extinguish a fire. The National Fire Protection Association has found that sprinkler systems reduce the risk of death in a fire by approximately 80%, and reduce property damage by about 70%. Despite these impressive statistics, the majority of residential homes do not have sprinkler systems, largely due to cost and homeowner resistance. Fire safety experts have long advocated for the inclusion of sprinkler systems in new home construction, and some jurisdictions have begun to require them, but widespread residential adoption remains a work in progress. Let us now talk about a topic that is both deeply ancient and profoundly modern: the use of fire in medicine. Fire has been used as a medical tool for thousands of years. The ancient practice of cauterization, using a heated instrument to burn tissue, was one of the earliest surgical techniques. Ancient Egyptian, Greek, and Roman physicians used cauterization to stop bleeding, close wounds, and destroy diseased tissue. The procedure was brutal by modern standards, performed without anesthesia, and often causing tremendous pain and scarring. But in an era before antibiotics and modern surgical techniques, cauterization was sometimes the only way to prevent a patient from bleeding to death or dying of infection. The heated instrument seared the blood vessels shut, stopping the hemorrhage, and the intense heat sterilized the wound, killing bacteria and reducing the risk of sepsis. Modern medicine has refined the use of fire and heat into far more precise and sophisticated techniques. Electrocautery uses an electrical current to heat a fine-tipped instrument, allowing surgeons to make precise cuts while simultaneously sealing blood vessels to minimize bleeding. Laser surgery uses focused beams of light, which are in essence concentrated fire, to cut, vaporize, or coagulate tissue with extraordinary precision. Lasers are used in eye surgery, dermatology, oncology, and many other fields. Cryotherapy, while technically the opposite of fire, uses extreme cold to destroy abnormal tissue, including cancerous tumors and skin lesions. And hyperthermia therapy uses carefully controlled heat to kill cancer cells, which are more sensitive to elevated temperatures than normal cells. Fire, in its modern medical incarnations, has become a tool of healing rather than destruction, a remarkable transformation of one of humanity's oldest and most feared forces. Here is a surprising fact about fire and food that goes beyond simple cooking. The process of smoking food, exposing it to smoke from a burning fire, is one of the oldest methods of food preservation. Smoke contains hundreds of chemical compounds, including phenols, organic acids, and carbonyls, many of which have antimicrobial and antioxidant properties. When food is exposed to smoke, these compounds coat the surface and penetrate the tissue, inhibiting the growth of bacteria and slowing the oxidation of fats. This preservation effect allowed our ancestors to store meat, fish, and other perishable foods for weeks or months without refrigeration, a capability that was essential for survival in environments where food supplies were seasonal or unpredictable. The flavor that smoke imparts to food is a side effect of this preservation process, but it has become one of the most valued and celebrated flavors in culinary traditions around the world. Smoked salmon, smoked brisket, smoked cheese, smoked paprika. The distinctive taste of smoke is a direct legacy of our ancestors' use of fire to keep food from spoiling. Fire has also played a crucial role in the history of transportation. The steam engine, which powered the Industrial Revolution and transformed the world, is fundamentally a fire-powered machine. Water is heated in a boiler by burning coal, wood, or oil. The water turns to steam, which expands and pushes a piston, converting heat energy into mechanical energy. Steam engines powered the first factories, the first locomotives, and the first steamships. They made mass production possible, shrank the distances between cities and continents, and fundamentally altered the economic and social structure of human civilization. The internal combustion engine, which powers most modern vehicles, is also a fire-based technology. Inside the engine's cylinders, a precisely metered mixture of fuel and air is ignited by a spark plug, producing a small, controlled explosion that drives the piston downward. This happens thousands of times per minute in each cylinder, producing the continuous mechanical power that propels the vehicle. A car engine is, quite literally, a machine that harnesses the power of thousands of tiny fires every second. Even in an age of electric vehicles and renewable energy, the internal combustion engine remains the dominant form of transportation power worldwide. Fire, once again, is at the heart of modern life. Now let us explore something that might give you pause: the vulnerability of modern society to fire. Despite all of our technology and safety systems, our civilization remains deeply dependent on fire and deeply vulnerable to its destructive power. Consider the electricity grid. Modern society cannot function without electricity. Our hospitals, water treatment plants, communication networks, financial systems, transportation systems, and food supply chains all depend on a continuous supply of electrical power. And as we discussed, a significant portion of that power is generated by burning fossil fuels. A major disruption to fuel supplies, whether from a natural disaster, a geopolitical conflict, or a supply chain failure, could cascade through the entire economy with devastating consequences. We have built a civilization powered by fire, and we remain at the mercy of fire's availability and behavior. Consider also the vulnerability of the built environment. Modern cities are filled with materials that burn: wood framing, plastic components, synthetic fabrics, paper products, flammable insulation, and petroleum-based materials of every description. A single fire in the right location, a high-rise building, a chemical plant, a fuel storage facility, can cause catastrophic damage and loss of life. The Grenfell Tower fire in London in 2017, which killed 72 people, was caused in part by flammable cladding on the exterior of the building that allowed the fire to spread rapidly up the facade, bypassing the internal fire safety systems. The tragedy exposed serious failures in building regulation and fire safety oversight, and led to a fundamental reassessment of fire safety standards for high-rise buildings in many countries. It was a stark reminder that fire safety is not just a matter of having the right equipment, it is a matter of having the right regulations, the right enforcement, and the right culture of safety. Let us now consider one of the most remarkable and little-known facts about fire: the existence of eternal flames. An eternal flame is a fire that burns continuously, sometimes for centuries, maintained either by human effort or by natural processes. We have already discussed the sacred fires of Zoroastrian temples, some of which have burned for over 1,000 years. But there are also natural eternal flames, fires fueled by natural gas seeping from the earth that have been burning for an extraordinarily long time. The flames of Chimera in southwestern Turkey is a natural gas vent that has been burning for at least 2,500 years. Ancient Greek and Roman writers described the flames, and they are believed to have been the inspiration for the fire-breathing chimera monster of Greek mythology. The gas seeping from the rocky hillside is primarily methane, produced by geological processes deep underground. The flames flicker and dance on the bare rock, burning day and night, in rain and wind, year after year, century after century. It is one of the most ancient and atmospheric fire sites on Earth, and it remains a popular tourist destination and a place of quiet wonder. There's a natural eternal flame hidden behind a waterfall in a park in western New York State that is kept alive by a small natural gas seep. The flame is only about 8 inches tall, but it burns continuously behind the veil of falling water, creating a scene that seems almost impossible, fire and water coexisting in the same space. Geologists have studied the gas seep and found that the methane is produced at a relatively shallow depth and at a relatively low temperature, which is unusual and suggests a geological process that is not yet fully understood. The flame occasionally goes out and must be relit by visitors, but the gas seep has been active for thousands of years, and the little flame behind the waterfall has become a beloved local landmark and a symbol of the enduring, surprising nature of fire. Now let us discuss a fact about fire that relates to the very air we breathe and the climate of our planet. Fire is one of the largest sources of aerosol particles in the Earth's atmosphere. When biomass burns, whether in wildfires, agricultural burning, or cooking fires, it produces enormous quantities of tiny particles that are lofted into the atmosphere and can travel thousands of miles. These particles have complex and sometimes contradictory effects on the climate. Some fire aerosols, particularly black carbon or soot, absorb sunlight and warm the atmosphere. Others, particularly organic carbon particles, reflect sunlight and cool the atmosphere. The net effect of fire aerosols on global climate is still an active area of research, and the answer appears to depend on the type of fire, the type of fuel, the altitude of the smoke plume, and the characteristics of the underlying surface. In the Arctic, for example, soot particles that settle on snow and ice darken the surface, reducing its reflectivity and causing it to absorb more sunlight and melt faster. This process is contributing to the accelerating loss of Arctic sea ice and the thawing of permafrost, both of which have far-reaching consequences for the global climate system. Fire, it turns out, is not just a local event. It is a global force that influences the chemistry of the atmosphere, the energy balance of the planet, and the trajectory of climate change. Here is a fact about fire that reveals something beautiful about the interconnectedness of life on Earth. Many species of birds have learned to exploit fire for their own benefit. In Australia, certain raptors, including the black kite, the whistling kite, and the brown falcon, have been observed picking up burning sticks from the edges of wildfires and dropping them in unburned areas, deliberately spreading the fire to flush out prey. These birds, sometimes called firehawks, use fire as a hunting tool, swooping down to catch insects, lizards, and small mammals that flee from the advancing flames. Indigenous Australians have known about this behavior for thousands of years and have incorporated it into their traditional ecological knowledge, but it was only recently documented by Western scientists. The deliberate use of fire by non-human animals is an extraordinary finding that challenges our assumption that fire use is an exclusively human trait. Other animals have developed remarkable strategies for surviving fire. The Australian bush thick-knee, a ground-nesting bird, remains motionless on its nest during a fire, relying on its camouflage and the fact that the fire front passes quickly. Burrowing animals, including wombats, rabbits, and various rodents, survive fires by retreating deep into their underground burrows, where the temperature remains relatively cool even as the surface burns. Many species of insects have evolved to detect and respond to fire. Certain beetles in the genus Melanophila, known as fire-chasing beetles, have specialized infrared sensors on their bodies that can detect the heat of a forest fire from distances of more than 50 miles. These beetles fly toward the fire because their larvae develop in freshly burned wood, which is free of the chemical defenses and competing organisms found in living trees. The beetles mate and lay their eggs in the still warm wood of the burned forest, giving their offspring a head start in a competition-free environment. It is a remarkable example of evolutionary adaptation to a recurring environmental disturbance. Let us discuss one more remarkable adaptation: the fire-resistant properties of the giant sequoia tree. The giant sequoia, which grows in a narrow belt along the western slopes of the Sierra Nevada mountains, is the largest living organism on Earth by volume. Some specimens are over 250 feet tall, more than 30 feet in diameter at the base, and over 3,000 years old. The sequoia's bark can be up to 2 feet thick and is composed of a fibrous, spongy material that is extremely resistant to fire. The bark contains very little resin, which means it does not readily ignite. When a fire does burn the surface, the thick bark insulates the living cambium layer beneath, preventing lethal damage to the tree. Giant sequoias have coexisted with fire for millions of years, and like the Serotinous pines we discussed earlier, they actually depend on fire for reproduction. Fire clears the forest floor of competing vegetation and thick leaf litter, exposing the bare mineral soil that sequoia seeds need to germinate. Without fire, the forest floor becomes too shaded and too cluttered for sequoia seedlings to survive. The suppression of natural fires during the 20th century actually harmed sequoia populations by allowing shade-tolerant competitors to crowd out young sequoias. Today, land managers use prescribed burns, carefully controlled fires set deliberately by professionals, to restore the natural fire cycle and ensure the continued health of sequoia groves. Prescribed burning, also known as controlled burning, is one of the most important tools in modern fire management. The concept is simple but counterintuitive. You fight fire with fire. By deliberately burning small areas of vegetation under controlled conditions, land managers reduce the accumulation of dead wood, leaf litter, and brush that serves as fuel for uncontrolled wildfires. This reduces the intensity and severity of wildfires when they inevitably occur. Indigenous peoples around the world have practiced controlled burning for thousands of years, using fire to manage landscapes, encourage the growth of useful plants, improve hunting conditions, and reduce the risk of catastrophic wildfires. In Australia, Aboriginal burning practices, known as cool burns or cultural burns, have been used for at least 50,000 years and are recognized as one of the most sophisticated land management systems ever developed. These burns are conducted during cooler, moister conditions, producing low-intensity fires that clear underbrush without killing large trees or sterilizing the soil. The result is a mosaic of burned and unburned patches that supports high biodiversity and reduces the risk of large, uncontrollable fires. Modern fire agencies are increasingly adopting prescribed burning as a key component of wildfire management, but the practice faces significant challenges. Smoke from prescribed burns can affect air quality in nearby communities, leading to public complaints and regulatory restrictions. There is always a risk that a prescribed burn will escape control and become an uncontrolled wildfire, and the window of weather conditions suitable for safe burning is often narrow, limiting the amount of burning that can be accomplished in any given year. Despite these challenges, fire scientists are nearly unanimous in their view that prescribed burning is essential to reducing the risk of catastrophic wildfires, particularly in fire-prone ecosystems where decades of fire suppression have allowed dangerous levels of fuel to accumulate. Now, as we approach the end of our journey through the world of fire, let us consider something philosophical: the dual nature of fire. Throughout this documentary, we have seen fire as a creator and a destroyer, a healer and a killer, a servant and a master. Fire cooked our food and expanded our brains. It forged our metals, fired our ceramics, and melted our glass. It powered our engines, lit our cities, and connected our continents. But it has also burned our homes, consumed our forests, poisoned our air, and taken our lives in numbers too large to comprehend. Fire is not good or evil. It is not a friend or an enemy. It is a force of nature, indifferent, implacable, and governed only by the laws of physics and chemistry. It does not care about our intentions, our plans, or our fears. It simply burns, consuming whatever fuel is available for as long as conditions allow. Our relationship with fire is the longest and most consequential relationship in human history. It predates language, predates art, predates religion, predates agriculture, predates civilization itself. Fire made us who we are, literally, biologically, neurologically. And it continues to shape our world in ways both visible and invisible. From the power plants that generate our electricity to the internal combustion engines that move our goods, from the controlled burns that manage our forests to the cooking fires that prepare our food, from the candles that light our places of worship to the cremation fires that return our bodies to the earth. Fire has been with us since before we were fully human, and it will be with us for as long as our species endures. The challenge that has faced every generation of human beings is the same challenge that faces us today: how to harness the power of fire without being consumed by it, how to use its creative force while managing its destructive potential, how to live alongside a force that can warm a nursery or incinerate a city with equal indifference. There is a line attributed to an ancient proverb that captures this tension perfectly. Fire, it is said, is a good servant but a bad master. When we control fire, when we contain it in a furnace, a stove, a lantern, a carefully managed, prescribed burn, it serves us faithfully and well. But when fire escapes our control, when it breaks free of its boundaries, when it grows beyond our ability to contain it, it becomes a force of almost unimaginable destruction. The history of human civilization is, in many ways, the history of our ongoing negotiation with fire. We have built our world upon its power. And we must never forget that the same power, if misused or neglected, can take that world away. As we close this documentary, take a moment to look around you. If you are in a building, look at the walls, the furniture, the electrical wiring, the light fixtures. All of these things were shaped in one way or another by fire. The steel in the beams was smelted in a furnace. The glass in the windows was melted in a kiln. The electricity flowing through the wires may have been generated by burning gas or coal. The paint on the walls contains compounds derived from petroleum, which was itself formed from the ancient remains of organisms that once powered themselves through the slow, internal fire of cellular respiration. Fire is everywhere. It is woven into the fabric of our built environment, our economy, our culture, and our biology. It is so pervasive that we rarely notice it, so familiar that we take it for granted. But fire deserves our attention, it deserves our respect, and above all, it deserves our understanding. Because the more we understand fire, its science, its history, its behavior, and its power, the better we can harness its benefits and protect ourselves from its dangers. Knowledge is, and always has been, our best defense against fire. And perhaps in a deeper sense, knowledge itself is a kind of fire, a light that illuminates the darkness, a force that transforms everything it touches, and a power that once kindled can never be fully extinguished. Fire, the oldest companion of humankind, the force that made us who we are, and the force that will continue to shape our future, for better or for worse, for as long as flames continue to burn. Thank you for joining us on this journey. If you enjoyed this documentary, please subscribe to the channel for more content like this in the future. Leave a comment telling us which fire fact surprised you the most, and share this video with someone who you think would find it as fascinating as you did. Until next time, stay safe, stay curious, and never underestimate the power of fire.